So I've had a few questions now about how I implemented pathfinding into my tactical RPG in Godot. And first of all, I would recommend for anyone interested in the subject, especially if you're new to Godot, to check out the Tactical RPG Movement series by GDQuest, which is also what we'll be using as a base for this project. I'll be linking that series in the comments or in the description below. So check that out if you're interested. And otherwise, we're just going to move on to expanding this system to make the pathfinding a bit more robust. And in particular, I'm going to show you how to deal with variable movement cost for tiles. Because as we can see currently, we can move our characters around, but these tiles, they are only, each one of them costs the same amount of movement. So we're always assuming the movement cost is 1. And the only obstacles we have here are the other characters, which you obviously can't move through. But we're going to be expanding upon that, and hopefully the system is going to be intuitive and simple to use. I'm going to be assuming that you know a little bit about how Godot works. You're comfortable with the inspector and know more or less where to find things. And also that you understand some basic programming fundamentals, although I'll try to explain what I'm doing and why, make it as easy to follow as possible. So even if you're not totally confident in your programming, I hope you can still get something out of this. Future me would also like to interject here and say that these things are difficult, and even having coded things like this many times over already, I made several mistakes in the process of recording this as well. So if you get stuck and you're confused, then don't get frustrated. Leave a comment. I'll try to help as best I can. And now on with the video. So first of all, let's move on here. Open up the map scene. And in the inspector here, we're going to click on the tile set. We want to add some more tiles here to help out, or to define different movement costs here. And I've edited the tile set that comes with the GDQuest project, but I've added a little extra tile here to mark an obstacle that will be the Godot phase here. And we're also going to select this bush here. I'm going to make a new tile out of that. And this is going to be a tile that costs additional movement to move through, but it's not impassable. So you're not going to be able to move as far as you would walking on like normal grass, for instance, but it's not going to completely prevent you from walking through it either. And then we're going to add the Godot face here as another extra tile, and that's going to be an impassable tile. So now that we've done that, we want to go back to the tile set here. We also want to add a script to this tile set. And new GD script. Actually, go back there. Save that. Put it in here, I guess. Put it in there with the background. And we're just going to name this tile set extender. What you name it doesn't really matter, as long as you know what its purpose is and the naming makes sense to you. So this, for this, we're just going to add one export variable, which we are going to call movement data, and that would be of type dictionary. And now, what that does is when we go back here into the editor, click on the map, open up the tile set again, we're going to see a new set or a new property here in the inspector on the right, called script variables, and in there we have our movement data, which we just defined. So now we go back in here to tile set edit, and clicking on or pressing down Alt will show you these numbers. These are kind of the IDs that identify each tile. And so for example, this grass tile here and the flowers, the grass, those that's an atlas tile with the key 1. So we're just going to add here, we're going to add a new entry into the dictionary, and the key is going to be of type int. We're going to make that 1. Actually, we're going to make that 0 because there's actually a hidden tile in this tile set that's underneath this atlas tile. That's just a single piece of grass, or like a single tile grass that might cause some issues if we don't define that here as well. So we're going to go back here. So we're going to add type int 0, and the value of that would be 1. So that's the movement cost of moving over that tile. And we're going to do the same for number 1. That's also going to have a movement cost of 1. I'm going to add that in here as well. And then for this bush, we're going to keep things simple and only use ints here because, or integers here, because as I think anyone who's worked with floating point numbers knows, there's bound to be some errors when you work with that, and we're just going to keep this as simple as possible for now. But do know that if you need more granular control of the movement cost, then you can use any type you want here. So here, the new key int, that would be tile 2, and we're just going to make that a movement cost of. And finally, number 3, which is our Godot face. Going to add the key 3, and that's going to have a value of, let's make it just a very high number that you're not realistically going to reach. You could mark that in other ways, for example as in -1, and then deal with that in the code as a special case, but we're just going to keep things simple, as I said. So this will, for our purposes here, it's going to work, but of course, depending on what your project's needs are, you might want to change some things about my approach here. So now that we're done with that, we're going to move on to accessing the data of this, the data that we just defined here. So next, let's move on here to that map itself. We're going to add a script here to the map. Just call it map.gd, that's fine. And for that, we're just going to onReady. Let's just first see if we can even access the data we just defined. So we're going to print. So this means as soon as the node loads in, it's going to execute this function. And for now, we're just going to see if our dictionary is there and has the values we want. So we're just going to print tile_set, that's accessing the tile set we just added a script to, and then we're just going to access the property movement data, which we just defined in the script here. And now, when we run the project, we can close this window already. And now we can see here in the console, the values we just defined are here and accounted for. So then the next step is we're actually going to want to, I guess, convert the tile set that we have, or the map that we have, into next we're going to want to actually get the movement cost of any single cell in the map. So for that, let's actually create a variable here for the tile map itself. Let's just call that movement data, and we're going to assign onReady. We're going to assign that here. So now the map itself always has movement data. There we go. So this is going to, we're always going to have a reference to the movement cost of a particular type of tile in the map itself for easier access. So next we're going to want a representation of the map in terms of each tile's movement cost. And to do that, let's make a new function called get movement costs. Where it's going to pass here for now, so the editor doesn't complain. And for this we want an argument, which is the grid, which is something defined in the GDQuest tutorial or here in the game board. We define this grid resource, and that's what we're using here because that contains the actual size of the map. Because the tile map here, it can actually be bigger than the actual game area, I suppose, or the actual size of the grid. So just to make sure we don't get any unnecessary data, we're just going to pass in the grid so we can use its size as a variable. So now we're going to iterate. So we're going to iterate over the width and height of the map. So for y in range, grid.size.y. Actually, we're going to have a new, let's see, var movement costs, and that's just going to be an empty array for now. And now for y in range. Okay, so for each row on the each row in the grid, we're going to append. A new array, and then for the width of each row, we're going to append the movement cost of that tile. So for x in range grid.size.x, we are going to first we need to actually get the tile. So the var tile equals, and since we're extending the tile map class here, we have a method called getCell, and we're just going to get the cell at coordinates x, y. So that gives us the numerical ID of the tile, which is also what we used as keys for this dictionary here. So the movement cost is just going to be movement data.get tile. And now we're going to append that to the movement costs y that append movement cost. So now we're going to append the movement cost of that tile to the list. And when all that is said and done, we can just return the movement costs. Okay, now that that's done, we can move on to the game board. Okay, so the game board is where the magic is going to happen. So first, let's just on ready. Actually, first we want to make a few changes here to the main scene. We're going to go over to the game board, and for the grid, since we don't actually have like a camera movement system here, we're just going to make the size of the grid the actual visible area, which in this case is 16 by 9 cells. Just to keep things simple, and so we don't get any weird results because of unassigned tiles and the like. And now we can go back here to the game board. Click on the script here, and now, actually, there's one more thing we want to do. Let's just move the map so it's child of the game board. That's just going to make it a little bit easier for us to access the map itself, which we can do here by adding an onReady variable. Let's just call that map. It's going to be a type tile map, and it's going to be there you go. With the $sign, we can access a child of a node very easily. And then let's see, let's just start with the ready function here, and we're going to print map.get movement costs. And actually, let's go into the map. Oh, yeah, we already removed the print statement there, so let's run it. Oh, actually, oh, we're missing a bracket there. Now, oh, of course, sorry. Yep, we need to pass the grid here as well. And now we can see a row of ones, or a few rows of ones, and that's because we haven't actually edited the map yet. So let's go back here to the map and add some tiles. Let's take the whole first row, nothing but obstacles, and the whole second row, nothing but bushes. That should help us see if our code is working as intended. And as we can see, it is. So now we have the corresponding movement cost of each tile here. And that's all the setup we need to actually code our pathfinding, which we're going to do next. Now, I'd like to preface this by saying that this is the quick and dirty solution, and that if performance is a concern for you, then I would look into using C or C++ to implement what we're going to do next. But I'm not going to do that in this tutorial because I'm going to try to keep this as simple as possible, and sticking to GDScript is, for that purpose, the ideal way to do this. But keep in mind that if your project grows and matures and you start to notice performance issues, then there is a solution for that, and then I would look into how to implement data structures and code in C and C++ for Godot. But for a prototype or for a quick small project, this should give enough. This should be performant enough to not cause an issue. At least for my current project, I haven't had a need to move over to C or C++ yet. Although that is probably in the cards as I get to a point where optimization becomes an actual concern. But for now, we're going to stick to GDScript and try to keep it as simple as possible. So let's get started with this. First, we're going to need kind of a base element, I guess, that we can insert into our priority queue or into our linked list. And for that, we're going to create a new script. Let's make a new folder here, just call it data structures. And in there, make a new script, and we'll call it, we'll call that, let's say, a linked node. Again, what you name it isn't terribly important as long as it makes some kind of sense. So for the linked node, call it class name linked node, and we don't need a ready function for that. So for this, we're going to have three values. We have a value, or we have three cut. For this, we're going to have three properties. First is the value. This will be in our pathfinding example. It will be the coordinate on the map, and then we want a priority for it of type int. Of course, if you're using float for your movement cost, then you'd probably be using float here as well. And then we have a variable called next. And next, basically in a linked list, every node has a link to another node. In this case, it's the node following it on the list. So the first node would have a reference to the second node, the second one to the third, and so on. So you can always access the next node from the current one. And then we want a function called init. So this basically means when we create a new node, this is when we create a new linked node. This is the function where we define the value or the properties of the node. So we want, let's call this node value, for example. Yep, this is what we pass on for the value. That's a vector 2 because it's going to be the position of the node. Then priority and next node. And for that, we're just going to have a equals null at the end. Oh, sorry, I'm missing a comma here. And basically what this means, the equals null means is if we don't, when we pass parameters to the, when we make, or cut. What this means is, what this equals null means is that when we create a new node, if we only pass 2 parameters to it, and don't pass a third one, then the value of this will default to null. And if we pass in a third parameter, then then we can, define, then it takes on that value. So here we just want to, okay, so value equals node value, priority equals node priority. Actually, I'm going to stay consistent with how I name my things. So I'm going to use underscores instead of camel casing. Again, you can use whatever system you want for naming your variables and all that, as long as you stay consistent with it. So priority, value, and next. Okay, so now we can easily modify or easily create okay, so now we have the constructor here ready, and now we're just going to want to create some setters here. So we have set value, value is vector 2. We have set priority. And set next. Okay, and that's all we need for this part. So next we're going to move on to creating the priority queue itself. So to do that, we're going to create a new script again. We're going to call that PriorityQueue. Going to name the class. Okay, so now we're going to move on to the priority queue itself. future me would like to interject again to say that what we're doing here is the way the priority queue works is that we have basically a long chain of nodes where we only ever have access to the first one directly, but each element in that queue is linked to the element that follows it. So we can traverse through the queue by going through each node one by one. And the way we're going to implement this, these nodes are always going to be sorted based on a priority value. In this case, they're going to be sorted from lowest priority to highest priority. And this will be very useful later on, as we'll see, when we get to the actual algorithm itself. And I'm just basically adapting code from what Geeks for Geeks article about how to create a priority queue in Python, and I'm just adapting that to GDScript, and I'll be linking that article down below as well in the description. So there's also examples in various other languages down there as well, so C and C++ at least, I believe. So it's good to check out if you want to find out more, I suppose. So we're going to need a few variables here. Front. This is going to be the front node of our linked list. So this is what we're going to retrieve when we access this list. And then we're going to want new node and temp. These are just helper variables we're going to be using to perform the operations we need. And then we want an init function, like we did with the node. And for that, we're just going to make front equal null. Then we want a function to check if the list is empty, or if the queue is empty. And for that, we're just going to return front equals null. So we're two of those, yeah. So what we're doing here, essentially, we're just comparing front to null to see if and returning the result of that. So if front is null, we return true, else we return false. And then we need a push function, which actually inserts an element into our queue. And for that, we're going to pass on two variables, which is the value or the node or the cell where we want to push into the queue, and priority, which is in this case going to be the distance of the cell from our position, which if it doesn't make sense now, it will hopefully make sense when we actually get to writing the pathfinding algorithm itself. So first, we want to just check if the queue is empty when we insert something. Then the front node is just going to be a new node with the value and priority we have here as parameters. And that's, as simple as that. We don't need to do anything else there. Else, if our current front node's priority is higher, because we want to the path or the node with the lowest cost, we're going to sort this list from lowest to highest priority. If you for some reason wanted to do it the other way, all you need to do is flip this greater than symbol into a less than. So we're going to make a new node and call that linked node. So linked node new, and this one, this new node is going to have it's going to be inserted into the front of the queue. So our current front node is going to become the next node for this new node. if that makes sense. Next, what we want to do is that if the node we're entering has a priority that is higher than our current front node's priority, then we want to traverse down the queue, going from the lowest priority upwards towards the highest priority, until we find the right spot. And the right spot is going to be where the priority of our new node is lower than the next node's priority. So what we're going to do is we are going to let me see. First, make use of the temp variable we defined, and that's going to be for the time being. It's just going to be our front node, and then while temp.next. So as long as there is a next node in the queue, we are going to see if our new node's priority is less than the next node's priority. If it is, then we break our loop because we found the right spot to insert our node. Otherwise, temp becomes the next node down in the chain, and then we go through the loop again until we either reach the end of the queue or we find the right spot to insert our node. Once we've done that, we can just create a new node again, so this is going to be a new node with the value and priority we pushed into the queue, and the next node being whatever temp.next was at the end of our loop. And then we're just going to make that there, temp.next equals new node. So now that's it for the push function, I believe, which means we now need a way to actually get our node out of the queue. So that's as simple as if the queue is empty, we just return. Otherwise, we're just going to make use of the temp variable again to get the value of our current front node. Then the new front node is going to become the next node down the chain. And at this point, the original front node is essentially no longer there. It's out of the queue because there is no longer any node that references it, and it's not our front node anymore. And then we can just return that node. And this is how the queue works. We just all we need is to get out that first element, and for that first element to be sorted. So now we can go here to the game board. Here we have the old flood fill algorithm. And now we can go to the game board. And here we've got our flood fill algorithm from the GDQuest tutorial, but we are going to replace that. So we're going to finally get around to actually coding the Dijkstra's algorithm, and it's going to have the same parameters here as the flood fill algorithm. And now what we want out of this is we want make a variable called movable cells, and we're just going to immediately append our base cell to that. And then we can return this here so the editor stops yelling at us. Okay. And now, apart from that, we are also going to need a few other variables. See that I get everything we need here. All right. So we want 3 arrays here: visited, distances, and previous. And then we also want, actually no, yeah, that's all we need. So visited is just going to be a 2D array that's going to keep track of which cells we've already looked at while we're running this algorithm. And the reason we use this is because the way the Dijkstra's algorithm works is that once we actually find a path to a cell, we already know that is going to be the shortest path to that cell. So if the algorithm gets into a situation where it needs to look at a cell again, we can just compare against this table to see if we've already visited that cell. And if we have, in that case, we don't need to do all the computation that comes after because we already have the shortest path to that cell. This distances table is just going to be another 2D table which shows the distance to each cell, which depending on your needs may be useful, may not. If you don't think it's going to be useful for your needs, then you can just omit this table. The same applies for this array here, previous, which is also a 2D array. This one is a little bit more complicated to understand, but or not complicated necessarily, but less intuitive, I suppose. But what it boils down to is that each cell within this table will show you which cell you have to take to get there using the shortest path. Okay, now that we've explained that, we can once again we're going to iterate over the width and height of the grid as we did earlier, and we're just going to put empty arrays here. And for x in range, grid size.x. For visited, we're just going to initialize the table with false for every cell. Oh right, I think I already did this off screen. But yeah, I defined a constant here called max value. This isn't actually the max value, but or max value you can have with an integer, but for this purpose it's fine. It's just going to be a very large value. That's all we need to care about. So yeah, this max value here is what we're going to use just to fill in these distances. So we append max value here. And finally, for previous, we are just going to append null. Because for now, we don't have paths to any cells. And then what we're going to do is we're going to make a new queue, which is the priority queue we defined, or that we made here earlier. Oh, sorry, I'm missing an equal sign there. Okay. And then we're just going to push our initial cell. So this is the cell our unit is standing on that we pass on as a parameter. We're going to push that into the queue. And this one has a distance of 0 because this is where we're starting. So obviously we don't need to spend any movement to reach this cell. And we're also going to mark this here. And then we're just going to define a variable here for use later called tile cost. Here I am again in editing, and I'm sorry for the abrupt cut here. I made some errors, and when I fixed those errors, I forgot to actually re-record this segment, or part of it. So I got to do part of it over, and I added this extra variable here that I didn't in the original take, called distance to node, that we're also going to be using later. And from here, we'll just keep going, and hopefully that didn't bother too much. We want a while loop, and it's going to be while not queue.is empty. So as long as there is still a node in the queue, we're going to keep looping. And within the loop, we're going to take out the front node. We're going to mark it as visited, because obviously we've seen this node now. So it's going to be marked as true. And then we're going to make use of this directions constant up here that was defined in the GDQuest tutorial. That's essentially just a series of vectors that correspond to each of the directions, so up, down, left, and right. So for direction in directions, we are going to add the direction to our current node. So essentially we're going through all of its 4 neighbors. And then, of course, we want to check if it's within bounds. And if it is, then we're also going to see if we've already seen that node, in which case we're just going to continue. Otherwise, and what continue does is it just goes back to the beginning of the loop, to the next iteration. So it's not going to go through the rest of the code, but it's still going to finish the loop, unlike break, which would just break the loop entirely. And then we're going to use this tile cost variable here, which I may have actually defined that during a cut. So we have these 2 variables here, tile cost and distance to node, that are going to be very helpful here. So for the tile cost, we just look at our movement costs. I may also have defined that off camera. So we're going to go here to the ready, in case I did. So in the ready function here, we're going to, first up here, we're going to just define the variable movement costs. And in the ready function, we're going to use the get movement costs function to get access to the movement costs. And I'm just going to store it as a variable. And I'll cut this out if I've already done that earlier. And then we're going to go back to Dijkstra's. So yeah, tile costs. We're just going to look at the coordinates .y, coordinates .x, and then we can calculate the distance to this node, which is going to be the current node's priority plus the tile cost. After that, we're going to mark this as visited. There we go. True, not pure. And for the distances, we're going to, of course, use or mark in our distance to node in there as well. After which we can do this. So if distance to node is less than max distance, so as long as the node is actually reachable by our unit, we're going to mark the previous tile, which is the tile. Basically, we're marking the tile we used to get here in the previous table, which is of course the current node's value. And then we're going to append this new node we're looking at to our list of movable cells, because we know we can reach it. After which we're going to push that same node in here using our distance as the priority value. And that should be it for this. So let's go back here to our main scene where I've constructed a little map. Can't see the overlays. Oh yeah, I'm going to change our map's z index to -1. And now we can actually see things. Oh, and that is also not working because I believe, yes, we need to change the method here from get walkable cells to Dijkstra. And now we have working pathfinding, including automated movement cost for the tiles. So you can see we can't walk past these Godot faces, but we can walk around them just fine. And walking through these bushes is a lot slower than walking elsewhere, as expected. So yeah, that's the basics for how to get pathfinding like this working. You can, of course, we had some additional. If we go back here to our Dijkstra function, we have these distances and previews as arrays that we fill out as we go along, and those may be useful for you. So for instance, this previous array here, that can actually be used to reconstruct the path that the algorithm found to that node, which will also be the fastest path available to that node. But that's something that's outside the scope of this tutorial, considering this has already been going on for a while. But if you do have questions about that, you can either look up more about the Dijkstra's algorithm on your own. There's a lot of good information about that online. But you can also drop me a comment and I'll try to clarify things. And that's just applies in general for any questions or issues you might have. As I said earlier, there's bound to be errors and problems as you try to work this out, especially if it's your first time doing this. That's perfectly natural, and just don't get discouraged. And don't be shy about asking people online for help. There's a lot of resources out there to help solve problems like this. I know this is a very confusing and messy topic, and that I definitely am not the best person to explain it to you, but hopefully this is at least enough to get you started and thinking about these problems. And thank you for watching.